Okay, folks, welcome back. Thanks for coming back. uh, though, if you didn't, I guess I'd just go on to dinner and not worry about it anyhow. But uh, I'm just being honest here. uh, let's uh, let's shift the gears now and kind of take this modern scientific method piece and talk about the dilemma of when is a difference, but also the dilemma that has to do with uh, how we can never really know for sure whether things are what we think they are. And, a great deal of it has to do with uh, what's called measurement theory or true score theory. And so I'm going to go back over to out of the piece out of Trocum that had to do with uh, measurement era, true score theory. Get up here. Okay. Uh, if you, whenever we measure something, uh, it doesn't matter how we're measuring it. If we're measuring it with an instrument, or we're measuring it with um, a scale or an observational checklist, or whatever it is we're measuring, or whether we're applying a coding scheme to qualitative data even. Whenever we are measuring something, there are always two components to it. And so, for example, with and as Trocum talks about, there's the X represents the score, or the measure, the score itself. Let's say it's a temperature of 101. Okay. Uh, Part of that 101 is true, the true measure. But unfortunately, a part of it is also error. Now, error could be related to how we measure, the actual instrument itself, limitations in the scale. There's all kinds of places error can come from. And we could deal with that because, like any other randomly occurring thing, it is normally distributed. So we could predict what the level of error would be. I mean, with some clarity, we could say we're 99% sure that the error is this amount. And if you think of the term margins of error, that's kind of what they're referring to roughly or generally, is that, we know this error exists. We just know that we're not going to worry about it too much most of the time because it's random. And so it's normally distributed, and it will be distributed around the true score. So, most of that's going to occur right at the true score. Unfortunately, we also know that not all things are random. And if they're not, if there are other things that could be happening that are not random, that would have a systematic influence on the score, we call that systematic error. And that's really what we're looking for in statistics, is the level of systematic error. Now, I'm not going to go through his discussion of random error and all that, but I think it's useful to look down here at these little curves and graphs that he does. If this blue curve, this blue arc, is the true score. That represents the true score. Let's say in a group of people, their true score is represented by this arc. That's purely random. If the error is purely random, this green arc, it's a little bit wider arc because we know there's some play in it, there's some error in it. But the mean and the high point occurs at exactly the same place. And so that's why most of the time we take for granted that what we observe, the score we observe, is actually the true score. Because we know the random error, is random, and so therefore its mean is going to be the same as the true score mean. So we don't have to worry about it. Okay. Now, systematic error, on the other hand, if there's something going on that reacts differently to different individuals, let's say for sake of argument, it works differently with males and females, even though we're not looking at differences between males and females. And let's just say the the red era, the red scale here, is that systematic error or the influence of gender. And the blue scale is the true score. It's still the T piece of the equation, the true score. So now the means are different. And that difference in mean is referred to as bias. And so we know that systematic error creates bias, which we can also, translate and say it creates an effect that may have been caused by something, the agent of the systematic error, gender, whatever it was. But that's what we're always wanting to know. We're wanting to know what is the ratio, at what point or do we have systematic error that would create enough bias to create a difference, to create a different effect. Now, then he goes into a whole discussion about reducing measurement error and all those sorts of things. And it's always good to triangulate and do all those things to reduce error, but no matter what we do, there is going to be random error. And if there's any effects going on, there's going to be systematic error. Now, does it rise to the level of where it's meaningful? I don't know. We have to kind of work through the stats to figure that out. Whether it's a significant difference, a significant bias, or not a significant bias. Questions before we? I mean, I've taught courses on measurement error, so we could go forever, but take a lot of equations. But anyhow.
I have a question. So how does effect ever affect the true value, or is it always captured in the systematic error?
That's a good question. Let me think of how I want to answer one. The answer is yes and yes. Okay. The effect is always in the systematic error. Sometimes that's not enough difference from the true value to be meaningful. And that's where this notion of meaningfulness comes into play that we'll get to eventually. I mean, if let's say we spend $1 million on some program in an elementary school to improve reading scores, and we discover that this program does have an effect, and it clicks up reading scores, 2 months. is 2 months growth in reading scores worth $1 million? Or would we be just as beneficial taking $1 million and, you know, buying 5 reading teachers or whatever? So yeah, it becomes meaningfulness at some point. But yeah, the systematic era is always moving away from the true score in some way. But it's just a matter, is it enough of a difference to be really meaningful? And that's what we have to figure out, you know, in the statistics. Does that help? That
I think so. So the true score really is like the mean of the normal distribution.
yes.
Okay.
Yeah. Yeah. That's exactly what it is. It's the mean of the normal distribution of a randomly occurring event. Yeah. Is the true score. And somewhere there's a theorem on that and a proof on that, but it's in a book that I don't want to look at, and you don't want to hear it. So, okay. Right. Ever since George Olson retired, I don't have anybody to talk statistical proofs and stuff with, but I kind of like it that way too. It's interesting stuff when you're starting your career, but when you're on toward the back end of your career, it's lost interest somehow. Some of the detail of all that. You just want to understand how it all works, how it all fits together, and so you want to know more of the generic kind of elements of it as opposed to the little nitty gritty detail pieces that you can argue over a lot. So yeah, okay, all right. So what does that put us at? Okay, I'm going to do this on my little overheady thing here. I don't know why it's a lovely shade of blue. Maybe I should figure that out. I don't know, but it's a nice shade of blue, and maybe it's the blue pen. That's what it. Yeah, it is the blue pen. I guess I should get a red pen, and then we'd have a lovely shade of red. But so you've got 2 pieces of error, 2 pieces of potential error. You've got the. Come on, focus up. Focus up. Why is this thing not focusing? Okay. Well, okay. It's supposed to focus on the pen, which it's not doing. Okay. Yeah.
It looks okay on my end.
It doesn't?
It does look okay.
Okay. I don't know
I
why
mean,
it's fuzzy on here, but maybe it's the share. That's what makes it. Yeah. Okay. Whatever. Yeah. So you got 2 pieces of error. You've got random error, cosmic dice, whatever you want to call it, and you got systematic error. Okay. Now, every single statistical procedure that you will run across, will have embedded in it a ratio of systematic error to random error. Whether you're doing t-test or ANOVAs with an F statistic, or even if you're doing a correlation with an R, whatever you're doing, whatever statistic you're doing, F, chi-squares, which is actually interesting because it's not, it's a categorical data. So you don't really have a norm or a mean, but even that works this way. But every one of them will have a formula. The basic idea of the formula is that there's systematic error on top and random error on bottom. Now, where do we get those, folks? Where do we get those things? We use an estimate for random error. And we use different estimates. We use things like standard deviations and standard error of measurements and standard error of means, standard error of difference. In other words, we have different ways of estimating the random error component that goes on the bottom. We kind of know what that looks like, and we can estimate it pretty well. And what goes on the top is observational error, which we can calculate from the data. Now, at infinity, so if we were at infinity, that's a rough infinity, but you know, I have bad arthritis, so it's a rough infinity. Let's say at infinity, all these ratios here would be normally distributed. And we could talk about the likelihood of a ratio occurring at different points. We could talk about the likelihood of a ratio that's over here. And we could talk about the likelihood of a ratio that's over here. And so we could put actual probabilities on the likelihood of a particular ratio appearing at a particular point. And we'll look at the standard normal distribution a little, well, not today, but we'll get very first thing into that next time. And with that standard normal distribution, we can know exact ratios. We can know exact probabilities. And for each one of these statistics that we might do, whether it's a T or it's a chi-square or it's an F or it's an R or whatever it is, and there's a bunch of them, all of them, they will all have unique distributions because we're not at infinity. And for example, some of those are they can fold over on each other. So you can only, if you know one value, you know the other value. And we'll get much more, and we'll talk much more about that next time. I don't want to confuse you with all that stuff. But the only thing that's important to know here is that every single statistic uses this ratio between systematic error and random error to determine that statistical value. And all of those statistical values can be put on a distribution that eventually becomes normal, although in the area that we use it in, it's not most of the time. And we can predict the outcome of a particular value of ratio. And so we can be 95% sure that there's a real difference. And that's the standard that we work at most of the time. We want to be 95% sure there's a real difference. We just come at it backwards, but we'll talk about that next time. And so actually the logic of statistics is inanely simple. I mean, it's pretty straightforward, is that we have this idea of randomness, which leads us to the central limits theorem, which leads us to normal distributions, which then we jump over and we think about the nature of error, nature of measurement, and we realize that error has a distribution too, and random error has a normal distribution, very predictable. Systematic error, not so predictable, but we can talk about the relative size of the systematic error versus random error. And there are all kinds of little factors there. There's N, how big the samples are, and what effect size really matters. Is 2 points worth thinking about, or is it important to have a 10-point difference, or is 2 points, even though it might be significant, is that meaningful? And so there's a lot of interpretive stuff that takes place in doing quantitative analysis. You'd think it'd just be hard numbers, okay, yes or no. Well, no, it's more than yes or no. It's yes, but, or no, what if, and so it's not as clear as those folks back in the 19th century had hoped it would be. At least not in the social sciences. Why not in the social sciences? We can know temperature. We can know a lot of physical qualities, characteristics. That works well for science. We cannot know most of the things we're interested in around humans. We can't know IQ. We can't know perception. We can't know, affective behaviors. We can't know those things. We attempt to measure them with imperfect instruments. And so the IQ test was really designed, if nothing else, to help us figure out how to prove eugenics. That was one of the primary reasons we did. Alfred Binet developed the IQ test. He was trying to help prove some of the science behind eugenics. Didn't work out too well, but the IQ test was stuck. So now we have this thing called IQ. We don't know what it is. We have no clue, but we have it. We think it's important. SATs were developed to be an admissions device for scholarship students into Ivy League schools, to see which poor kids were smart enough to, survive at Ivy League schools. It doesn't predict any success in school whatsoever. And so a lot of universities using the opportunity of the pandemic to get rid of SATs or ACTs or any of those scores, because they don't tell us anything. But they create a hell of an industry. And that's the primary reason they still exist. It's an industry with a lot of lobbying power. But they really don't mean a whole lot. Because a lot of we can't open up the brain up here and see what intelligence looks like, or any of those things in social sciences we're interested in. We can't measure them. And so we create devices to try to measure them. We create scales and instruments and, Likert scales. You know why we invented Likert scales? So we could be able to take things that weren't quantifiable and put them on a scale that we could treat like a quantity. And so you know, a lot as we become aware of a lot of these things in, you know, the last century or so, we realize that, you know, we can't ever really know for sure, but we can estimate and we can predict, and that's about the best we can do. We'll never know cause and effect, surely. We'll know with some level of certainty, 95% certainty cause and effect, but we can never really know. And don't forget the other thing you're supposed to take away from this. You can never know how individuals will react. Because statistics is a group analysis and not an individual analysis. All right, that should either have bored you silly, have driven you to tears because you hoped you were going to have a nice clear answer, or I don't know, something else. Plus, we're all tired. So are we pretty good right now? Okay, not yeah. Think about if you have questions or you have things that you want to know. You know, give me a yell, send me an email, and I'll be glad to kind of deal with that. Next week, and I'll put these up hopefully tomorrow, if I once I get moving tomorrow morning. I'll put up an article that I want you to take a look at. It's one that I was a part of a few years ago. It's one of those articles, you know, if you're an academic, you write a lot of stuff, but every now and then you write one that seems to have sticking power that you, yeah, I guess this thing was, I don't know, 10, 12, 15 years ago. I don't know exactly when it was. I've been here 30. So I guess about 14, 15 years ago, we published this article in a review and research and practice in learning disabilities journal, which at that time was the big international journal that everybody tried to get in. And I linked myself up with one of those mega stars that, you know, was in early on the Special Ed Act and stuff like that. Esther Minskoff. I don't know if you've ever heard of her. Esther is a giant in the field, and she was a good friend. And we wanted to put a grant together. When we wrote this grant, and we got a pretty good chunk of change to deal with undiagnosed learning disabilities among university students, and a program that we were pushing, a demonstration program using peer coaches, peer mentors. And it was, you know, it was a nice study. We thought it turned out well. We published it, we got it written, worked up, published it. And I would say last count, I had about 1,500 citations on it in different pieces. And it's been 15 years, and every year I'll get somebody who'll call me up and say, well, do you have the original data? I'm going, yeah, sure I do. I got the original data from basically 17 years ago. I mean, I got it right here. I always keep it handy just in case somebody calls. No, I don't get that cynical with them, but I do tell them, no, you know, the data is lost. But yeah, I can tell you kind of our findings and stuff that we didn't put in the article, you know, that we observed, but we can really felt comfortable putting in the article and things like that. But it was one of those seminal pieces that a lot of people use. And so, you know, you get one of those every now and then. You get one that hangs out there. I got another piece of work that people want. There's a chapter I wrote in a book in 1984. And people want to know if I still have the manuscript. I'm not even sure I still have the book. I mean, it's probably in a bookshelf somewhere over there. But, you know, it's kind of like, okay, I'm not quite sure. I remember a few things about that. I mean, yeah, I wrote it, but, you know, that's been a while. It's been 30 some years. It's kind of got, but yeah. Yeah, it's funny when you write things, you think they'll be end up on a shelf someplace, nobody will ever pay attention to them, but you'll be amazed how many people stumble across stuff that some of which you wish you had forgotten, but some of which, you know, you would like to remember because they were pretty good. And I'll give you the one that was pretty good. I think that was a nice one. And it has the advantage of being fairly straightforward and fairly simple, mathematically and statistically. And so we can kind of use it to ease in, but it's also a mixed methods piece that's got a pretty strong qualitative component to it too. So we'll start with that, and I'll give you. We'll talk. I'll put it up. Well, maybe I'll put it up tonight. See if I can get it up tonight, and then I'll give you some questions in a day or so. That these are things I'd like to talk about with, and then we'll get into some of the quantifiable stuff and look at where some of the analysis came from and why we did a certain thing as opposed to some other thing, and that sort of stuff. And that'll be the pattern pretty much, except we'll ease ourselves into a fairly deep dive into some statistics. Any of you, do y'all use SPSS, or have you used SPSS? So you're familiar with SPSS. I actually have two ways to go. I can do SPSS, or I can also do a program, a freeware program that's out there, that's supported by like 400 different universities around the world. It's called JASP, JASP. And I'm using it for a lot of stuff now. So, but we'll do both. We'll do the SPSS piece. And then if you're not familiar with SPSS, I'll do a little quick and dirty thing about JASP so that you can see how that works. I mean, it was developed to be a teaching platform because it's not as detailed and nitpicky as SAS or SPSS or R or any of those. Yeah. But yeah, we'll stay in SPSS some, and then we'll do a little bit of the JASP piece because that's kind of what I'm playing with these days because I think it's really neat. Okay. Any other questions?
I have a
thoughts?
question for my peers. The SPSS that we downloaded last semester, how long does our license last?
Typically a year.
Okay.
Or is it a
So
semester?
I ended up using the UDesk and doing it through there each week. So I never even downloaded the paid version last year. I just went through the UDesk each week to do the assignments.
Oh, okay. Yeah.
Oh.
Yeah, you can do that. Yeah.
Sorry. I actually deleted it from my computer because it seemed to be weighing my computer down really badly. But I mean, it was
Well, you
pretty
can,
simple.
do you have any information on the UDesk piece? How did you?
I'll just send you the link.
Okay. Yeah.
That you just have to be logged into as you learn. I mean, there's a little learning curve of just because it's like it brings up on your computer the interface of like a brand new computer.
Mhm.
So you have to kind of get in that mindset that you're in somebody else's computer. I know that sounds a little complicated.
Yeah.
Let me see if I can pull it up right now.
Yeah, I used both. I used UDesk and then I also had a downloaded version on my bigger computer, but I never had problems with using UDesk. Once
I haven't done that, so yeah, maybe I need to learn to do that too. Yeah.
So
I'm putting the link in the chat.
Okay. All right.
hopefully that answers your question. Long way.
All right. I'll pull that out and yeah. Okay. All right. So it's just UDesk, App State, EDL. Okay.
And you just click to log in and everything.
Okay. All right. We'll do that. I'll play with that a little bit, see if I can get the hang of that. So don't worry about, getting it. I mean, it's not like we're going to learn every little intricate thing of it because we're just going to basically pull a data set up and say, okay, well, here we're going to answer this question. We have to do this, we have to do that. I will do some stuff later on in Excel because we do have to talk about cleaning data and recoding data and things like that. I find that much easier to do in Excel than to do it inside of a stats program. Excel gives you a lot more things, more tools to work with, because Excel is basically Excel and Access all rolled into one these days. So, you know, you can do a lot of stuff with Excel, and that's where I do most of my data cleaning is in Excel, and then I'll dump it into something to play with it. Yeah. Okay. So we're good. All you have to do is read the article. Just the article. That's all you got to do. And there'll be, I'll offer a few questions just to kind of give you some clues about what maybe to look for and things like that. Yeah. We're going to be talking about a lot of elements of that article too. We're going to be talking about the kind of the structure of the article, because there is sort of a common structure that they all go through. And different editors have different notions about that, but in general, this one's pretty standard. And the other thing that we'll need to talk about is conceptual framework, because that's the thing that you'll have in sort of building your research ideas. That's the thing that you'll have the most confusing difficulty with, is thinking about conceptual framework, because you have to have an entry place from the literature to get into the research you want to do. It's a good way to say it. And so we have to find connections that will allow you to ask the questions you're asking in your research. And typically you ground those in the knowledge base, whatever the knowledge base is for that particular topic area. So lots of fun to play with. We got lots of stuff to play with. Okay. All right, folks. Y'all go have a good evening. Maybe I won't put that article up this evening. That way you won't even worry about it. I'll put it up in the morning. And I happen to have it handy. You know, it's right on. It's one I'm proud of. So I keep that one handy a lot. So we'll go from there. Have a good evening. Stay safe. And I'll see you all next Wednesday, I guess. Yeah. Night. Good ask App State EDL.